Okay, welcome back everyone. So in this video, again, we're going to continue our discussions on E2 reaction. Realize that this is a really topic. There are like several aspects of this reaction that we need to understand and talk about. And these are important because we'll come back to these concepts again later, like in chapter 8 and 9. We will still be coming back to some of these things, to understand what happens in those chapters. So what we're going to do in this video is discuss E2 reactions. And we're going to look at a few aspects of E2 reaction. Okay, and then I'll go into some more details of the mechanism of the E2 reaction. Okay, what else do we know about the mechanism of an E2 reaction? So the first thing about E2 reactions is that it is a regioselective. There's a regioselective reaction. So the reaction has regioselectivity to it. And we've already seen this in one of the examples, one of the earlier examples that I did, but I'll just quickly go over it again. And then look at another aspect of it. Okay, so let's go back to this example, or before we go there. So what does that mean? Okay, what does that mean is some products are favored over others. Okay, some products are favored over others, and in the particular case of E2 reactions, this depends on the beta hydrogen that is abstracted or deprotonated. Okay, abstracted or deprotonated. So depending on which beta hydrogen is deprotonated, some products are favored. So for example, I think we looked at this example before, but let's say in this example, when 2-bromobutane, this molecule, reacts with butane, reacts with sodium methoxide in methanol. Now realize that this molecule, and there is heat also, so you're trying to promote E2 reactions. So realize that in this particular example, there's our alpha, and with anytime you see E2 reactions or you're thinking about E2 reactions, the first thing you want to do is identify all your betas, because realize that every beta hydrogen would give you an E2 product. It will give you a unique E2 product. Okay, so we have alpha there, there's beta here, and there's beta here, not identical. So let's say this is beta prime. And we saw this example earlier. So we have H beta prime, we have H beta here. And so this reaction is going to actually give us two possible products. Actually, I'm going to change this molecule a little bit because I want to go into something else later, actually. So I'll change this molecule out a little bit by including a methyl group, another methyl group here, okay? Because that would keep it cleaner, actually, and I can talk about some of those other things later. So we still have one H beta prime here. So there is a beta and there's a beta prime. They both have hydrogens. So when the E2 reaction happens, the base can deprotonate either one of these two. So I would encourage you to actually push some mechanism, push some arrows and then draw the products. I'm not going to do that here, but the two products that I would get, or that we would expect to get, are this plus the other product is going to be that from the two reactions that are possible. From the beta, H beta, we will get that product on the right, and the H beta prom will give us the product on the left, okay? So these are the two products possible. Now, since we already know the stability of alkenes, what we know is that the more stable alkene here, this is going to be the major product, because that's a tri-substituted alkene and this is a mono-substituted alkene. So that means in this particular reaction, based on the stability of the product, okay, based on the stability of products or stability of alkenes, one product is favored. So we can say that this is a regioselective reaction, because notice how the product selectivity depends on which H beta is deprotonated, like which region is the H beta coming from. So essentially what's happening is H beta prime is deprotonated more often than H beta. That is why we are getting this product selectivity. We're getting the more substituted alkene as the major product and the less substituted alkene as the minor product, okay? So this selectivity that we are seeing, where the more substituted alkene is the major product and the less substituted alkene is the minor product, this selectivity is called a Zaytsev product distribution. Or we can call this, actually to keep it simple, we can call this a Zaytsev elimination. So what happens in Zaytsev, so that's the name of the person who actually first identified this trend, you know. So Zaytsev elimination, more substituted alkene is major product. So that's the Zaytsev elimination. And this is what happens in E2 reactions, because the more substituted alkene is the major product. Like, you know, that is more stable. The more substituted alkene is more stable. And so that tends to be the major product. But sometimes, you know, organic chemists, they might want this product more for something. Maybe I'm trying to like make a pharmaceutical drug or something else. And what I want is, I want that minor alkene, the minor product, more than this major product. So if I do this reaction, and let's say, I think the textbook has the numbers for this. So if I get 71% yield of this product and 29% yield of this product, okay? So that means if I start from this alkyl halide and do this reaction, I only get I get only 30% roughly of that alkene product. But I probably want to do something with this alkene, like I want to do something else, take this on to like another step, the kind of reactions that we will learn in chapter 8 actually. So then it would be good if I can actually make this in a higher yield. Okay, if I can actually maybe switch these numbers, if I can make 70% of that, or 30% and 30% of this, or even better, if I can go like 80 or 90% of that and only like little bit of the other one, you know, that would be really good, because then for every mole of the reactant that I'm starting with, I'm getting more moles of the product that I want. So how would we do this? That's the question. Okay, there has to be a way to do this. And again, the answer to all of this actually lies in the mechanism. Okay, what happens in the mechanism? So let's go ahead and draw those arrows now. Actually, I'm going to draw those arrows now. So how do we get these products? is the question that we're trying to look. So how do I get this major product, the more substituted alkene? So the way that happens is the base deprotonates H beta prime. Okay, so if the base deprotonates H beta prime, then that would give me the major product that I have here, the more substituted alkene. And if the base deprotonates H beta, that would give me the less substituted alkene. So if I want to make more, and if I want to make more of this less substituted alkene as a product, what I want this reaction to do, or what I want the base to do, is to actually get H beta more times, right? Remove that more times than it removes beta prime, because right now what's happening is it is removing H beta prime more often than it removes H beta. But I don't want that. I want it to remove H beta more often than H beta prime. Okay, so we have to change something about this reaction so that the base would actually remove H beta more than H beta prime. So how are H beta and H beta prime different? What are some differences that you can cite? So if you look at H beta and H beta prime, their environments, you know, where they are located, what sort of things do you see? Hopefully you can notice that H beta is a primary hydrogen. Okay, it's connected to a primary carbon. H beta prime, on the other hand, is connected to a tertiary hydrogen. Tertiary carbon. So H beta prime is a tertiary hydrogen. So one is a primary hydrogen, one is a tertiary hydrogen. And now tertiary hydrogen, it has other groups around it. That means there's going to be more crowding around it, whereas the primary hydrogen should be much free. Okay, so when we exploit that, the differences in the environment, to actually make more of the less substituted alkene? The answer is yes. Okay, the answer is yes. So if I change the base out, okay, if I change the base, and if I go from, I'm going to use the same alkyl halide. We have H beta, beta here, this is alpha, this is beta prime. We have H beta prime. Okay, and what I'm going to do is, instead of using methoxide, I'm going to use a bulky base, like a bigger base. So I'm going to use something like potassium with O minus, but now this O has 3 methyl groups. So this is a T-butoxide. This is a third butyl group. So it's called potassium T-butoxide. I will try to write it here. Okay, so this is potassium third butoxide. This is an example of a bulky base. This is an example of a bulky base, like a big base. So if I substitute this small base, carbon with 3 hydrogens attached to it, carbon with 3 methyls attached to it right now, that's the difference that we're talking about. If I substitute that out, so I'll have to change the solvent now. So my solvent should be the conjugate acid of that base, and we're going to heat this also. So if I do this substitution, now my base is really big, it's bulky. And so what that would do is, the base would, or is less likely to go for H beta prime, because it's a tertiary hydrogen. Okay, so this is a tertiary beta hydrogen. This one is a primary beta hydrogen. So the base is less likely to go for H beta prime and then give us elimination product, which would be this. Instead, since H beta is a primary hydrogen, there's more room around it, okay, it's roomier around it, it is more likely to go and deprotonate H beta. And if that happens, that means I am making a lot more of the less substituted alkene. So the way we differentiate these alkenes are more substituted alkene, less substituted alkene. So this is the more substituted alkene, and this is the less substituted alkene, okay? So now we can actually favor the more substituted alkene. So it turns out you get a 28% yield of this and 72% yield of the less substituted alkene now. Okay, so it's a 20, about a 30 and a 70. So we've almost reversed it. Okay, if I want to make it better, what should I do? I should make this base even bulkier. Okay, I should make that base even bulkier. So I'm going to write that last reaction over here for lack of space. So it turns out, and this is in the textbook, this is page 295. Okay, so page 295, if we do the same reaction, write the molecule similar. So if I do the same reaction, but use a much bulky base now. So let's say what we're using is a potassium with oxygen, and now instead of 3 methyl groups, we have 3 ethyl groups now. So we made it even bigger actually. If we do this reaction, we're going to get this plus that. Okay, the more substituted alkene and the less substituted alkene, and it turns out the numbers are 8% and 92%. So we can get almost 90% of the less substituted alkene, which also realize that the less substituted alkene is the less stable alkene. So it's not the preferred product from an E2 reaction, but we make it preferred by playing around with the base. Okay, we can change the base, make it bulky, and that helps us make more of the less stable product in some sense. So it's not the thermodynamic product, it is a kinetic product now, if you want to connect it to chapter 6. Okay, so it's not the thermodynamic product. So we can do this reaction. And so this selectivity, where I'm going to erase all of this. Okay, this selectivity where the less substituted alkene, let me check, Hofmann, Hofmann elimination. So this kind of reactivity is called a Hofmann elimination compared to Zaytsev elimination. So in a Hofmann elimination, the less substituted alkene, which is the less stable product, is the major product. The less stable alkene or the less substituted alkene is the major product in a Hofmann elimination. Okay, so that's regioselectivity in E2 reaction. So let me show you an example of how we would exploit this. Okay, So now, let's say if we have a molecule, and you're going to see these things like written in like several different ways, but let's say we have a molecule where we have very bigger. Let's say that's an alkyl halide. Okay. And for this alkyl halide, you have two conditions given. And what you have to do is you have to write the major product. Okay, that is what we're doing here. Predict the major E2 product. That is what we're doing here. And one of the conditions is NaOET with ethanol and heat. The other condition is potassium T-butoxide. That's how we write. This is essentially potassium O T-butoxide, that thing. Okay, that's how we write that. And T-butanol with heat. So we're trying to see what happens in both cases. So we have the alkyl halide alpha, beta, beta prime. H beta, you have H beta prime. So if we remove H beta prime, we are going to get a double bond over there. If you remove H beta, we'll get a double bond over here. So since we have ethoxide, no, again, ethoxide is not something bulky, okay? Because, well, it's bulkier than methoxide, but it's a straight carbon chain. We think about bulk when everything is like basically spreading out in space. That's like, it's like sterics. So it has to go out in space. It's just a straight chain, carbon chain. So we don't have to treat that as like a bulky thing. So in this particular case, when we do the reaction, the major product when we use, or in this particular case, it's a Zaytsev elimination because it's not a bulky base. So the product that we are going to get is going to be this. That'll be our major product. This is a Zaytsev product. And I'm only writing the major product because that's the question, predicting the major product. And this is Hofmann product. So that will be our major product. The less substituted alkene would be the major product with the bulky base. The more substituted alkene would be the product with the less bulky base. Okay, so that's the regiochemistry of E2 reactions. In the next video, we're going to talk about stereochemical aspects of E2 reactions.